Hello and welcome to another episode of the Oxford Online Maths Club. My name's James, it's just me on the stream today, and Pascal's triangle, of course. Other names for this triangle do exist, but it's a triangle we keep going back to over the season of the Oxford Online Maths Club. This is actually the last episode in season 5 of the Maths Club. I'm loop us back to something we did right at the start of Maths Club, but don't panic, season 6 is only a few weeks away. We take a couple of weeks off for the Easter holidays, and then we're back in 3 weeks time. So just to get that out of the way, this is the last episode in season 5, but season 6 is coming as well. Hi to Erin and Kai and Jamie and oh gosh, so many people in chat. Hi to Herb. Hi to people who are joining us in live chat. If it's your first time on the stream, then hi, welcome to the live stream. You can join live chat underneath at Vvox. There is a link somewhere on the bottom of the screen down there. There's a link for you to find that. If you're watching the replay on YouTube, then feel free to fast forward a bit because it's going to take me a moment to get to the point. You're also able to watch it, I think, at like double speed if you watch it on the YouTube replay. Fun stuff been happening recently. I've done some maths talks. I met someone came up to me and said, "Hey, I know you from the live streams." That was pretty cool. Hi, Jamie. I also did these massive events in London with loads of different universities, and Oxford get one tiny corner, and people come over and meet people who work at Oxford. We met a lot of people there. If I met you and I promoted the live stream to you, I'm sorry, that was a bit weird. Here we are. We've got Pascal's triangle on the screen, and we're going to talk about something from previous episode, but don't worry, there's no need to see that episode first. I'm going to explain it again. We had some unfinished business there that we're going to come back to. But first, I'd like to start how we always do by checking how everyone's day is going. I'm having someone straight in there with 5 stars. I'm having a 5-star day, I think. It's actually been mostly a day off, except for this. And this is almost like a day off. Somebody voted 1 star pretty quickly there as well, though, so I see you. Gosh, it's tough, isn't it? It's maybe the time of year when people start having mocks and start doing predicted grades and start thinking about university, and that's all a bit tough. I'm always looking out for people to vote 1 star or 2 star. Coming in now. I don't know if doing a load of maths right now is going to make your day better or worse, but either way, here's some maths. You don't have to understand it. There's no test on this. It's not going to be examined. Behind the poll, Miles in chat says, "This might be the part I studied, which would be fun." Yeah, a while ago we had some observations, and several people emailed me with their ideas and maybe a bit of proof about what they thought was going on. I'd like to try and pull some of that together now and show you not the full answer, but some of the answer to give you some ideas. Yeah, sorry to talk about A-levels. That was maybe not a very sensitive thing to do. Sorry about that. Average has come out. Oh, there's a lot of people voting 5 stars there. So people having a nice day. Hey, good to see you. Right, okay, that'll do. Let's do some maths. There we go. Yeah, Kai, sorry about that. Good, right, okay. So, reminder, Pascal's triangle. Wait, I'm going to take this question first because this looks important. It's a quick question about Oxford. Is it true that Oxford prioritises private schools more? I don't think we do. We are looking for people who are best suited for our maths course. Oxford takes fewer private school people than you might guess, especially maths. Maths is less private school than the Oxford average, still more than the kind of UK average. And that's maybe not a great thing, but overall I think maths is quite a kind of meritocratic thing. Right, cool, that was that quick question. Let's not do too much admission stuff now. I had this big event in London earlier this week. Right, I did admissions non-stop all day, it was brilliant. Reminder for people who haven't seen it before, Pascal's triangle, also known as the Chinese triangle, also known as the Italian triangle, lots of other different things, works like this. You write down the numbers 1 and 1, and the rule for all numbers underneath there is you add together the ones that are above, so you get 1, 2, 1 in this kind of diagonal pattern. So you get some 1s down the outside, and then in between the 1s you draw these kind of diagonal lines and you add together the numbers. So you get something like this, and the pattern I've put on screen is whether or not those numbers are odd or even. So in that top row they're both odd, but then this 2 here is an example of an even number. So I put a blue dot there, a darker colour dot there for even numbers. So there's a row here, 1, 3, 3, 1. I haven't shown you the numbers, but I've got this row here that's all green. That corresponds to this bit where it goes 1, 3, 3, 1. Is math and computer science more competitive than maths and stats? Oh, big news on maths and stats. As of this year, we're going to admit joint. So the thing you click on UCAS is going to say maths/maths and stats. We're just going to do all those applications together. So no direct applications for that course. People are going to be able to swap between them during the first year, choosing whether they're on maths or maths and stats in about the 4th term. Maths and computer science is a very competitive course. Yes, right, good. Really shouldn't do too much admission stuff. Okay, Pascal's triangle. There's this lovely pattern on the screen. It's maybe more complicated than you might guess. I'm not really sure what you should guess when you're asked which numbers in Pascal's triangle are odd and which numbers are even. But the pattern's really complicated. It's kind of great. There are these rows down here, look, where it's kind of all green. And we got quite interested in those on the live stream. I want to try and explain those later on. Rows where it's all odd. That's kind of interesting. And just below them, there are these rows where it's all even, except the ones. There have to be these ones on the outside, they're going to be there, but we have these rows in between where it's all even. And these kind of occur together. Because if you have this row here that's odd, then just afterwards you get a row that's got even numbers in between, because odd plus odd is even in between. And they signal, they signal the arrival of one of these big upside down triangles, because underneath you're adding together then even numbers, and even plus even is even, so you tend to get around here even plus even is even, so you tend to get these kind of downward triangle of evenness. Things underneath within that triangle tend to be even. Guys, got an explanation. There's an alternating row. That's a good spot. Alternating. Yeah, so these features really stand out to me because they signal the arrival of these massive triangles. So down here, look at this bit's brilliant. This kind of arrival of a massive triangle. And the triangles form this kind of nice structure. There's kind of a hierarchy of bigger and bigger triangles. They kind of point towards each other. So there's this triangle, and then this next one, and then this kind of huge one. And then that's pointing towards this even larger one. And they kind of form this nice structure with stuff going on in between as well, which reminded us. I want to use the past tense because we observed it before on the live stream. So I say reminded, but it kind of still reminds me of the Sierpinski gasket or the Sierpinski triangle, which is made by stamping out upside down triangles from a right way up triangle. When you stamp out the upside down triangle, you get these smaller right way up triangles, and then if you keep stamping out, you can keep making stuff. Cool. Is this like modular arithmetic, says someone anonymous in chat. Oh, my chat is not showing. There we go. Is it like modular arithmetic? Yeah, you could use modular arithmetic, if you know what that is, to keep track of the oddness and evenness. In a way, that's like saying, instead of working out these numbers and then rounding them, or then finding the remainder when you divide by 2 afterwards, instead of doing that, you can find the remainder when you divide by 2 as you go. So 1 plus 1 is 2, the remainder is 0. 1 plus 0 is 1, 0 plus 1 is 1. 1 plus 1 is 2, the remainder is 0. 1 plus 1 is 0, 2, the remainder is 0. If you keep taking the remainder on each row, then maybe you're doing something that feels a bit like, that's called modular arithmetic, I guess. It all works out nicely. So if you're writing this in your computer, then you might like to keep track of just the oddness and evenness like that. Hi, if you're late, we're just looking at Pascal's triangle, if you've just joined us. Pascal's triangle is made by adding together copies of the previous row. You've maybe seen it before on this show or elsewhere. We're going to try and explain what's going on with these odd numbers and even numbers. It's a really good question in chat. Are there more odd numbers or more even numbers in Pascal's triangle? So it depends. There's infinitely many of both, which is an unhelpful answer. So I guess you could maybe ask, down to a particular level, are there more odd numbers or even numbers? Down to maybe one of these interesting green rows where it feels like it's settled down. That feels like something we could do. Maybe not right now. Is it easy? It's not going to be fully easy. It's going to be okay, I think. can probably do that question. That's a really good question. I like that a lot. Right, okay. I would like to try and explain today, I hope this isn't biting off too much, I would like to try and explain where these rows happen, and not just for the number 2, where we're looking at the remainders when you divide by 2. I'd like to explain it for other numbers as well. A little bit vague there, but I want to show you some other pictures too. Let's look at some pictures first. So this is the picture when I take the remainders when you divide by 2, like oddness and evenness. Over here, I've got a picture for the remainders when you divide by 3. So here, this is looking at, this is the row 1, 1 at the top. I've done those in kind of pink colour, kind of pale orange, I guess. And then 1, 2, 1, I've put things that are 2 more of the multiple of 3, I've put in yellow. And then 1, 3, 3, 1, we've got these things, these are multiples of 3, so I've put them in pink. That's kind of 3 different colours for multiples of 3, 1 more or 2 more. So you've got these diagonals of 1s coming down here, and we've got a more complicated picture going on inside here, but we still get this massive row down here of things that are all multiples of 3, except the 1s. The 1s are not going to be a multiple of anything interesting today, but we've got a row here that's all multiples of 3, and I think I've missed one. Ah yes, there's another one up here, look. And another one up here. So this one we calculated. Everything in this row is a multiple of 3, except the 1s, because they're both 3. Okay, it's not exciting here, and then somehow it's more surprising down here, and then maybe really surprising that you get this. Almost feels like a coincidence that you get so many things that are all a multiple of 3. Not a coincidence, we're going to work out when that happens. Okay, so I hope this picture's enough to convince you that there's something going on that's similar between the 2 picture and the 3 picture. Some stuff's more complicated, but some stuff comes back again. I can still see some sort of upside down triangle pictures going on. It's more complicated image this time, but somehow I've still got this kind of hierarchy of triangles that build up to some sort of larger repeating pattern. You see, I've got these kind of small triangles here, and then bigger triangles here, and then maybe this huge triangle does something similar as well. Yeah, it is alternating above again. That's true. There's something going on just before. I suppose what could we say? If you're going to get a row where everything's a multiple of 3, then just before things would either have to be 1 more and 2 more, or 2 more and 1 more, or 3 more and no more, which would both be multiples of 3. Hang on. So all the pink things either come from yellow plus orange, or they come from pink plus pink. There's not very many different bits you can get with only 3 colours. There's not very many like small units of what could be going on if I sort of circle little units. Pink plus pink is pink, pink plus orange is orange, orange plus pink, let's see if I can find one of those. Orange plus pink is orange. It's these sort of small units of what's going on. That limited palette of small additions, there's only a few colours, there's only a few additions we need to work out, that's modular arithmetic. Only looking at the kind of small palette of what might be happening. And it saves you from working out like all the different numbers you might need to add together. Okay, I've got a picture of 4, different colour scheme. This one looks a bit different to me. This one generates some patterns, but it's not quite the same as the other one, right? I mean, it has to be different because these are the remainders when you divide by 4. So it has to be something different going on here. But also the upside down blue triangles aren't all the same. There's this upside down blue triangle here, sort of Oxford blue, but it's not the same as sort of this one because this one's got a yellow triangle inside it. There's sort of some distinctions between the different bits of it. The larger scale looks a little bit different. I love this. In chat, an anonymous person says the first one feels like a lower resolution of the second one. Yeah, I love that. So the kind of the bigger the triangles get, maybe the more high definition the triangles are. And whereas here's something different going on for 4s, something really complicated. I can't see any rows that are all multiples of 4, except the ones. Somebody's going to catch me out at some point because I'm going to forget to say except the ones. But I can't see any rows where everything is, I think it's dark blue for these multiples of 4. This doesn't work because the 6 is not a multiple of 4. And then further down here it gets pretty close to being all multiples of 4, but just sort of misses in the middle. And also down here, we've got this thing here, which is not what I wanted to see. It's not a multiple of 4. Aha! These patterns are really good, aren't they? Yes. Yeah, this is to do with binomial expansions. What happens if I draw this triangle in the real exam? You can draw it in the exam, I think. I'm not sure you get any sort of special. So you claim that this doesn't happen. And we've got hypothesis coming in chat. Gijol, Kai and Herb have guessed something that's true about 2 and 3, but not true about 4. So it's a good start. I've got some more evidence on my Miro board that we'll put together. There's another one where almost all 4 in between the 2. Have I missed one? Almost all in between the 2 I've labelled. Where are you looking? Oh, up here. Yes. Okay. This now looks like a sort of angry face. Which is also how I feel when I see this triangle that doesn't quite have any rows that are all multiples of 4. Yeah, there's some logic to where these are, but they're not doing it for me. They're not the same. Good spot, brilliant. Okay, I've got some more pictures. Just because once I set up my computer to draw these for me, it was quite easy to just change the numbers and draw more pictures. This is 5, and people in chat who said something about prime numbers, you'll have already noticed that 5 is prime, and look, there are these rows with these rows where everything is a multiple of 5 except for the 1s. I can only see a couple of them here. There's also some things that are quite close. Maybe that happens for all numbers, who knows? But then just before we get this lovely alternating row, and then a row that's all multiples of 5 except the 1s, and then a huge triangle again. And that gives it this quite nice structure, these upside down triangles. There's just something nice going on here, right? These multiples of 5 form in these kind of upside down triangles, stacked together, and then just the right spacing somehow to get this kind of big row, where all multiples of 5 like that. Huge triangle. And I can maybe imagine what it will look like going down. Well, I've got this kind of hypothesis, even though my computer gave up after a bit, I stopped it. But I can kind of imagine what that might look like if the big triangles are laid out like the small triangles. That wasn't the case for 4, there was something more complicated going on with what those triangles look like. But here the upside down triangles kind of look the same. Question in chat, did I use Python? No, but I should have. Hey kids, Python's pretty cool. Yeah, 4's pretty interesting. Question about international A-level. Oxford's position is pretty boring, we just treat it the same as A-level. I know you do exams at different times and slightly different topics perhaps or something, but we just count it. 5 is bigger than 4, yeah, cool. Powers of 5 maybe, so let's do this quick counting. So this is, if I count this as, this number in Pascal's triangle is the number 5, I think. This is number 10, 15, 20, this is the number 25. So someone spotted that might be something to do with powers. Good pattern spotting. Let's look at 6. Maybe imagine what you think 6 will look like. It looks like a mess. Here it is. There's too much going on here for me to get any ideas. Just so much complicated pattern stuff going on, right? There's these upside down triangles that are multiples of 6. So let's find out 1, 2, 3, 4, 5, 6. Yeah, 6 is the dark blue colour here. And there's this kind of big upside down triangle where almost everything is multiple of 6, but then the multiples of 6 turn up in this kind of more complicated pattern that I'm not even sure I can draw very accurately. There's then 2 small triangles, a very tiny triangle, 2 small triangles, a tiny triangle, 2 small triangles. What is going on here? This is crazy. There's so much going on that I have no chance of explaining where the multiples of 6 are in this picture. They're doing something really complicated that involves big triangles and smaller triangles, kind of in some sort of overlapping pattern. And we get this huge triangle, but I can't see any rows that are all multiples of 6. Maybe there's more coming. The patterns within the colours. So the patterns within the colours could be, there are some ways that the other colours are similar to each other. Yeah, so sometimes the other colours are similar to each other. I think that's not quite true on this particular picture though, because I think the red ones are a bit different. Or is it the 1, 2, 3? Is it yellow's a bit odd? Because it corresponds to 3? Yeah, 6 is a bit weird. Sort of weird here. 7's nice though. 7 has got these rows They're all multiples of 7 except for the ones, and some sort of nice structure going on here. I can see some nice predictable upside down triangles that are multiples of 7 coming through here. I don't know how I set this up, but it seems like the colour schemes are different in each one, but the multiples of n are always kind of the same colour. I don't think I did that on purpose, it's just one of those coincidences. That's a sort of nice picture going on here. And is there something going on in the other colours? Maybe. There's a colour scheme on here for the range of numbers between 0 and 7. Who knows? Okay. And I did not get to row 49, so we're not up to row 49 in this picture. I agree. I think that 49 would have been an interesting point to look at, because I guess my hypothesis is something like, in the 3 picture we stamped like 2 of these upside down triangles and then got the next one up. In the 5 picture we saw 4 of these and then got the next one up. In the 7 picture, I reckon we're probably going to need 6 of them and then get the next one up. And I don't really think I've understood how that pattern works or why it's happening, but that's my intuition. And it actually turns out if you generate a bit more and get down to the 49th row, then hey, there's a lot of numbers that are multiples of 7 in there. Let's write out that claim because it's a bit cool. So the claim is that the row that is 5 to the k for any k is all multiples of 5 except the ones. I've been calling them ones like that before. Okay, and also I suppose the kind of other claim that's kind of implicit in there is that other rows aren't like that. And it's really this second claim that I'd like to try and prove today, because the first bit's not too bad to check, and in fact I'm going to show you some techniques that will apply to that case as well. And more importantly, these techniques are going to work for other numbers other than 5. I think I'm going to try and stick to 5. Now, some people sent me some maths, and most people's maths used the formula for n choose r, which Kai has mentioned in chat as well here. And there's this sort of ugly truth, I suppose, that there's a formula for the numbers in Pascal's triangle. If you're in row R and you're looking at, that's a terrible idea. If you're in row N and you go R along, let's stop trying to describe this in words. The coefficient, one of the numbers in Pascal's triangle, it is the formula for them. The formula for them is this, which is not obvious. There's something to do with factorials. A factorial means take the number and multiply by all the numbers that are smaller than it down to 1. It's this kind of mad formula that gives you the numbers in Pascal's triangle. N is supposed to be the row number, and R is supposed to be how far along the row you are between naught and N. Let's write that down. This is sometimes called n choose R, or some people stack them together like this, n on top of R, like a vector, but it's not a vector. And there's this formula for it, so you can go and try and prove this using the formula if you like, and thinking about trying to prove whether things are multiples of 5 or not. That's quite a lot of work. I think it's a little bit ugly. Miles says a bit complicated, so Miles, I remember, sent in some stuff using n choose R stuff. What I'd like to do instead is to show you something that really goes into the n choose R. Okay, so first let's do a little bit to say why it's about choosing. What's Pascal's triangle got to do with choosing? So 5 minutes just to show you what Pascal's triangle's got to do with choosing. So the idea here is that you have n objects, or items, or beads, or sheep, or whatever, and you want to choose, select or pick R of them. And the idea is the order doesn't matter. We're going to make some sort of herd of sheep, and they're going to mix around. So It doesn't matter what order I pick the sheep to be in my herd. And this is subtle, but the order of the others doesn't matter. The sheep that I don't pick in my herd, also they can just mill around somewhere else, and they don't matter. So this is related to Pascal's triangle, because if I've got two objects, let's say, there are two ways to choose one of them. That is quite a boring statement, right? I could choose the first one, or I could choose the second one, and 1 + 1 is 2. Welcome to the Oxford Online Maths Club. So it's pretty boring. Maybe more subtle. There is one way to choose two of them, and there's also one way to choose 0 of them. So if you lay out those numbers, you write out these answers in the sensible order, and you have sort of 1, 2, 1. More interestingly, if you've got 3 objects, there are still one way to choose 3 of them, one way to choose 0 of them, but there are 3 ways to choose 2 of them. Here's how. Here's how I know there are 3 ways. I mean, I could go and list the 3 ways, or I could take my sheep. There are 3 of them. And here's what I could do. I could paint one of the sheep pink. It's fine. It's harmless to paint the sheep pink. It's just nice to look after them a little bit like that. And then I could think about either choosing the pink sheep, because it's cute, and then choosing one more of the others. Or don't choose pink, and then I'll have to choose 2 of the others. Either I choose sheep like this, or I choose sheep not including the pink sheep. I choose like that. Those are the 2 cases. That means that I need to do some adding. I need to add the numbers together, add the number of cases together. So in the first case, I choose the pink sheep, and then I need one more. I've got to choose that one from the 2 remaining sheep. That's 2 choose 1. So if you'll let me use this notation for 3 choose 2, I've got 3 sheep and I would like to choose 2 of them. People normally write it with like a superscript and a subscript for how I'm choosing them. I could either choose the pink sheep, in which case I will need 1 more from the remaining 2, or I could not choose the pink sheep, in which case I will need to look at the other sheep and choose 2 of them. So this is kind of inherent adding going on. That continues. And that's exactly the sort of adding we do in Pascal's triangle. So exactly the sort of adding we do for Pascal's triangle. So the next row down is going to be 1, 3, 3, 1, because that's how choosing works. There are 3 ways to pick 1 sheep, 3 ways to pick 2 sheep. Just list them: A, B, B, C, A, C. Yeah, and by symmetry, choosing 2 is the same as choosing 1, but also because there's this kind of recurrence relation, which is the link between choosing and adding. I think at school people get taught the link between choosing and multiplying quite quickly on. There's this formula about multiplying and factorials, but there's also this link between choosing and adding, which gives you Pascal's triangle. That continues. So it's not just right. Good. In general, I suppose you could say if I've got n objects, paint one of them pink, and then to choose r of them, either ignore the pink one and choose r from the remaining n minus 1, or choose the pink one and then choose r minus 1 from the remaining n minus 1. So in general, we get this kind of recursion relation of adding together the previous things recurring on the way down, and it's exactly the same thing as Pascal's triangle. Cool. That's the link between Pascal's triangle and choosing, because now I've got adding and I've got choosing. I haven't had to do any factorial stuff, so I can interpret this claim as something to do with choosing. Let me try and write this out properly. I think my claim is that How do I want to do this? Yeah, I think I want to do it like this. If n is not a power of prime p, then it is not the case. This is a bit confusing double negative, but sorry. So if n is not a power of prime p, then it is not the case that n choose r is a multiple of p for all r except the 1, so I need to sort of do rule r between 2 and n minus 1. So I need to rule out the n's. Do I mean 2? I think I mean 1. Yeah, I'm not looking at 0 on the left. Okay. Okay, I'm going to try and spend the next half an hour doing that, if that's okay. Let's break it down let's break it down. I want to make sure we get there together. This is what I'm going to be doing, I think, for the next half an hour. Gosh, I hope this is not too much. Once we've got this, it shows that most of the rows are not all multiples of 5, except for the ones at the edge. Only these powers are worth considering. It's not too hard to piece together a pattern and show that those rows actually behave nicely. And the method is going to generalize nicely to say something about 4 and 6 as well. Okay, just in chat to prove it using a recurrence relation, I'll do something a little bit different from that, I think. Okay, I want to dig into what n choose r really means, and what it means for n to not be a power of prime p. Let's break those things down. So I'm looking at not a power of prime p, because the powers of prime p are very interesting. They look like they're going to be the ones where everything's a multiple of p. The other ones are interesting to me, too. Everything's interesting to me, I guess. So this claim here, looking at the rows that are not like 5, 25, 125, those ones, I'm going to use the fact that n's not a power of prime p, and I'm going to interpret that as n must be equal to, how do I want to play this? Let's say it must be, maybe it's a multiple of p? Maybe it's a multiple of p? Maybe not. Let's say it's n times p to the, which letters have I not used? I haven't used a k yet. Some k, and for some n. So I want to try and take out the multiples of p from n. I want to look at it. I want to say if it's not a power of a prime p, it might still be a multiple of p. It might be a multiple of p squared, but it's not going to be just a power of p. So there's going to be some bit over here where n is not a multiple of p. Chat's just over the top of that. There we go. Okay. So maybe you could take out some factors of p. This is kind of a technicality. Maybe you can take out some multiples of p, but you can't take out only powers of p. There's something else going on here as well. There's some multiple of those. For example, if n is 20 and p is 5, then I've kind of got this like leftover bit. You can take out a factor of 5, but then you don't get to 1, you get down to 4. 20 is 4 times 5. I'm trying to work out if it's a good idea to just put in 20 everywhere. I think it's probably more confusing than it needs to be. Chat's catching up. Hey chat, what's happening? I turned up late. We're trying to prove this thing. I think I'm ignoring. Let's ignore n equals 1 for now, thanks. Hi, if you just got here, we're trying to prove something about Pascal's triangle. We've noticed that most of the rows are really colourful when you colour in the multiples of 5. You get these occasional rows where everything's a multiple of 5 except the ones at the edges. We're trying to prove that only happens sometimes, that most of the time, if n is not a power of the prime, p, then it's not the case that n choose r is a multiple of the prime p for all the in-between numbers. Okay. Let's look at this then. So this n choose r means choose r things from n. Okay, what do I need? I think I would like to look at first if n's not a multiple of p. There's this row going down here, which is a nice repetitive row. It goes, we've kind of exploited it along here. It goes multiple of 5, 1, 2, 3, 4 more than a multiple of 5, multiple of 5, 1, 2, 3, 4, not more than a multiple of 5. It kind of cycles nicely like that, going down that diagonal. That's n choose 1. There are exactly n ways to choose one thing from n. So this claim would include n choose 1. That's when r is equal to 1, but that's equal to n. Okay, so if n is not a multiple of p, then this is really obvious. Let's piece that together. I kind of hate it when people say something's really obvious after doing some work, but hey, okay, so let's step 1. If n is not a multiple of p, look at r equals 1. n choose 1 is equal to n, not a multiple of p. So we're done. Okay, so sort of, I shouldn't really say obvious, I should say easy once you know to look there. Start off with, if n's not even a multiple of p, then it's just hopeless. It's not going to be the case that everything's multiple of p, because not even the first thing is a multiple of p. Off to a full start. So n's got to be a multiple of p. That means that this k up here is at least 1. There's at least one multiple of p in there. That seems like a good start. We've restricted our attention to just the plausible candidates that might be all multiples of p. It's a little bit like we've ignored the ones down the edges, and then we've looked just on the row inside. That side. Just on the row inside, and we look, oh, only some of these are multiples of p, so if we're looking for a row that's mostly multiples of p, then we can ignore that one. I think this is the point where I'm ignoring the number 1. It's off topic. I write my letter P's like that because I work on fluid dynamics, and in fluid dynamics we also have the Greek letter rho, and P for pressure, rho for density, and I need them to look different. Don't worry though, there's no rhos today. But force of habit, I've now taught myself to draw my P's like the old letter thorn, but sadly not a thing anymore. Right, good, okay. We've got many cases left. We've got cases where n is a multiple of p. We're kind of in this other case. Multiple of p, but not a power of p. So I want to imagine what it's like to choose r things from n in that case. And I want to lay out n in a particular way. I want to imagine that we're choosing squares on a grid. Here's the grid. I want to lay out the grid so that there are n rows on my grid, and there are p to the k columns on the grid. Okay, so I'm in the 20 example again. 20 is still in the running because we've checked that 20 at least starts with a multiple of 5. I think it's the number 20, but so far we've only looked, let's zoom right away in, we've only looked kind of here. So we've seen that 20 choose 1, this first number here is a multiple of 5. Maybe this whole row is multiples of 5, we haven't looked across yet, so I'm going to try and look across now. Okay, we're going to think about choosing things from this grid by putting ticks in the grid, or blobs. Let's go ticks. So I'm going to choose, I would like to choose p to the k things, squares, what we're going to call them. P to the k here is 5 in my example. I guess there's a bit of a boring example where P to the k was worrying about powers, P to the k was just P, but hey, choose 5 things. This is a little bit like doing some sort of multiple choice test where I've chosen 5 of them, I suppose, but I'm choosing to tick in 5 boxes. I don't have to pick one from each column, I suppose. Nothing like a multiple choice test. I can just tick in 5 of the boxes. Okay, I claim that this is not, the number of ways to do this is not a multiple of P. And then we'll be done. If I can convince you that this particular element is not a multiple of P, what I'm doing is I've jumped over to the 5th item in the row. And if you remember the 20 row there, that's actually the one, it's actually the first one that's not a multiple of 5. I want to jump across to that item to look at choosing P to the k squares in this grid. There are lots of different ways to do that. So choosing 5 things here, I could choose all the things in the first row, I could choose things going down in a diagonal and looping round, I could choose most of the stuff on the left, I could choose just the first column and a few bits and bobs. Yeah, sure. Okay, I've gone for P to the k rather than P plus 1. What does k mean? K is being used here as the power of P in the prime factorization of n. It's a bit technical, isn't it? But we've convinced ourselves that we only need to look at the case where n's a multiple of P. Those are the only plausible rows that might be full of multiples of P. So we can pull out factors of P from that number. That's a helpful trick because it means we're left over with, we can always do that for a number to pull out its factors of P. I don't really know how many factors of P I'm pulling out and I don't really care, but I'm using K to keep track of that. I'm using P to the K to mean the kind of prime power bit of n. Pull out all the factors of 5 or whatever. You can always do this, so it's kind of a useful thing to do, to pull out all of the powers. Giving things names is a powerful technique. So at this point, I haven't really done anything with K. It's just been in there because you can do this. In a minute, I'm going to use the fact that n is not a multiple of P. That's going to be one of my tricks. Okay, to show you why, I need to go into the 3rd dimension. I've got a kind of grid, and I'd like to show you what I want to do with that grid. So I'm going to take a quick jump into the real world. Why am I choosing P to the k? I've had an idea about what these choices look like based on the real world. It sounds mad, but here goes. Okay, so I've got the grid in the real world over here, jump cut, and we're making choices of 5 things from this grid. Of course, there are lots of different ways I can do this, lots of different choices about how I choose 5 things, but the choices are related together in some sort of way. Let me show you what I mean. So if I tick some boxes, I'm going to tick 5 of these. What I can do is I can roll this up into a kind of pentagonal pyramid. So I can roll this up into a pentagonal prism, sorry, that's what those are called. I've got some glue here, let's stick this together. I can roll this up. If I roll it up and stick it together, then I can, so it started like this with the tick here, and then down, and then up, and then 2 in that column. But I can roll this around and then unwrap it to make a different pattern. Let me show you what that looks like. I've got a choice about where I cut it to unroll it. I could be boring and just uncut it where I stuck it to get back to the same pattern of ticks, or I could cut it somewhere different. You might like to think about how many choices I've got about where I cut it. I'm going to cut it here, I think. If I cut it here, then I get a new grid of choices, choosing 5 things from that grid of 20 squares. I get a different choice, a different one of the items from 20 choose 5. Let's go back to the board. So I guess the point that I'm making there is that we can rotate the board to get other choices. Now, you can probably use spatial reasoning or something to work out what these choices look like, what the relationship is. Let's maybe put a tick here and not there, and here, and here, and here, and here. You can do these rotations, and that gives you a kind of collection of these choices together. So there's loads of different choices, about 20 choose 5. Loads of different ways to choose 5 squares from 20, but you can rotate the board around like this to generate other ones. How many ways can I cut that? I think there were like 5 ways I could cut it, right? Yeah, 5 ways I can cut it. And then the question is, are they all different? Are they all different, or are they the same? And this is why I've been looking at p to the k. Because there's a special case. It does sometimes give me the same choice. Sometimes when you rotate the board, you get back to the same thing. Now, I want you to convince yourself that there's not very many ways that can happen. So what I want is for all of these cuts to be, different choices. Maybe I want that, maybe I don't. Anyway, that could be the case, right? That when I cut it, I get these different boards of 20 choose 5, one of the other possibilities out of 20 choose 5. But actually, if all of my ticks are in the same row, if all my ticks are in the same row, then rotation does nothing. So I've got this kind of gimmick, I suppose. There are these ways to, I've got this kind of gimmick of rotation. And sometimes that links together the items of this massive set of different boards I could draw, 20 choose 5, right? Massive set of different boards. Sometimes gluing them, rotating them, cutting them gives me different things. If it does, then it gives me this kind of nice, I don't really want to draw a massive pentagon. I think I am going to try massive pentagon of options with kind of 5 things in, and kind of rotation around, right? Rotation, keep rotating. And the nice thing is that either all 5 of those are different or they're all the same. That is subtle. I'm going to claim it here, but it is a little bit subtle. Either all 5 of those things are different or all 5 of those are the same. And the only way they could all be the same, let's break this down, is the only way they could all be the same is if I rotate it one step and I get the same thing. That would mean they have to all be all the columns have to be the same. And if all the columns are the same, they've got to have 1 tick in each, in the same place. So this gives us these nice chains of 5. What am I calling these? Grids or boards? Nice chains of 5 different grids, but some kind of loners. There are n loners. They don't rotate to give each other, they don't rotate to give anything else, they just rotate to themselves. Okay, can anyone see where I'm going with this? Yeah, it's a little bit like everything I talk about, isn't it? So, it's 5 types. I don't know how many of these there are. There are probably quite a lot because 20 choose 5 is pretty huge. Don't want to work out how big it is. But Apple's got it that there are these big pentagons, multiple of p. In these loops or chains. Multiple of p because each one is multiple of p, and putting them all together, multiple of p. But there are these n loners, and n is not a multiple of p. Ooh. Important word, not a multiple of p. People who've been following a bit will know that I'm now done, but I'm going to keep talking. Because what this means is that by looking at exactly this element of choosing exactly this element of Pascal's triangle, choosing exactly 5 things from 20, I can show, even though that number is impossibly huge, really, but I can show that it's not a multiple of 5 because I can partition everything up into these packets of 5, except for some leftover ones. Not very many leftover ones, and I know how many, and it's not a multiple of 5. So there's nice 5 packs, but some leftover ones. It is a little bit like some stuff we've done with some painting. Aha! Can they be the same? Could they be the same? Hey, one person says it's cool. Yes, that's what we live for. Can it be the same if the ticks follow some sort of up-down special pattern? Not even. Yeah, okay. So I have hidden something under the carpet a little bit. It's to do with p to the k. I've shown you a kind of spinner thing with just 5 sides. Really, I should have shown you one with about 25 sides to show that in the case that k is not 1, in the case that k is not 1, the spinning can get into some repeating patterns, but those patterns will be a power of p. There'll still be a power of p in the spiral. That's really subtle, and it's to do with the factors of the number of sides on the spinner. I've got some more spinners here. Am I calling them spinners? I should decide what words I'm using before I go live, right? So for this one with just 5 sides, there's no way out of this because when you rotate it, if you want to see exactly the same thing again, then you would need that one to be the same as this one. If you rotate it 2 steps, well, maybe rotating it 2 steps. You might expect maybe that could give me the same thing, but actually if you follow it round, rotating 2 steps again would have to give me the same thing again, and then rotating 2 steps again, oh gosh, would have to give me the same thing. And it turns out, eventually you follow that round and it turns out that all of the sides have to be the same. That is not the case if I've got 6 faces on my spinner, just to be clear. So this one's got 6 faces. And there you can do other stuff where you could have maybe some ticks on this face, and some ticks on this face, and some ticks on this face. And now when I rotate this, I only discover 2 sorts of tick patterns. One's where the ticks are in the odd rows, and one's where in odd columns, and one's where the ticks are in the even columns. I don't discover like a multiple of 6, I just find these 2 different things. And 2 is not a multiple of 6. So I guess this is a difference between 6 and 5. The 6 prism, hexagonal prism, has this kind of other pattern you can do on it, so that when you rotate it, you see different things, but not 6 different things. Whereas a spinner with 5 sides, you're going to see 5 different things. A spinner with 25 sides, you'll either see 25 different things, or you'll see 5 different things as you rotate it around. There's a thing going on here with the factors of the number, which is why primes are interesting, which is why we're talking about primes today. I would encourage you to explore it and explore what happens. It feels very simple, this idea about having a grid, rolling it up, rotating it, and unrolling it. But my proof really relies on the idea that these will all be different, or at least the number of different things will be a power of p, or a multiple of p, so that I can ignore all of them. The lovely thing about multiples of p is if you're trying to work out whether something multiple of p, you can ignore any multiple of p inside it. Cool, what's going on in chat? Yeah, there's a helpful chat note in chat. 6 is not prime. This is a pictorial way of showing n choose p to the k. Yeah. Let me show you one more time. In this example, n is 20, and p to the k is 5, and I've chosen 5 of the 20 things. But I'm exploiting the fact that 20, I know a way to draw 20 squares, right? You might be imagining 20 squares all in a row, and that's fine, that's how you can imagine 20 choose 5, but 20 you can draw it as a grid. That's why I went and tried to quite carefully pull out the factors. Because if I pull out the factors, I'm using this fact about how I can draw it as a rectangle and then build it into a spinner. Is this something to do with residues? Yes. Kai has got a helpful fact there. I have learnt a fact about 39. Good. Okay, so ways I think you could adapt this. I've proven maybe something a bit weird. I've proven that if n is not a power of prime p, I've proved that if n is not a power of prime p, then it's not the case that everything's a multiple of p in that row, except for the ones at the edges. That's maybe a bit of an odd thing to prove. You might have expected me to prove, aha, if you're using a prime number and you look at the prime power row, then everything is. And I want to leave that as homework. You can use this. You can use a similar version of this to prove that in the 6 case, you can use some sort of spinner arguments to say that, aha, if everything's going to be a multiple of 6, then you need to be in one of these rows, which is a multiple of 6. So you need to be a multiple of 2. And a multiple of 3. Now, nothing's a multiple of 2 and loads of things are a multiple of 2. Nothing's a power of 2 and a power of 3, so we're going to get it one way or the other. And the kind of key idea for why this doesn't happen in the 6 triangle is that nothing is both a power of 2 and a power of 3. So one way or the other, I'll be able to throw in, aha. This argument will be kind of useful in the 6 case as well. But I'm going to leave that as homework for people over the break in between series. Yeah, let's take questions from chat, because I think it came together quite quickly at the end. Off topic, can you take functions of non-integers? Choose functions of non-integers. Oh, I don't know, I've never thought about it. I don't know how you define them. Some sort of gamma function thing? Yeah, possibly. It's not obvious to me that those are not a thing. I reckon I could probably come up with a thing. Some people like defining factorials on non-integers using something called the gamma function. I've never thought about what happens for choose in that situation. Or maybe I have and then I forgot. Why is it always loners or generate different patterns? I did hide this a bit. So the loners are kind of obvious that they exist, because if I take this, I'm not going to do it in the real world, but if I take this and roll it up, stick it together, cut it, I'm going to get the same thing back again, right? All the columns look the same. Here there's a subtlety going on that if I've got just 5 columns, then maybe you can see that when I rotate it, I kind of have to rotate it by a factor of 5 squares along in order to get back to the same thing. Let's imagine that rotating it 2 squares, and this is just an example I suppose, but let's imagine that rotating it 2 squares gave us the same thing. Then I'd rotate it by 2 squares and I'd get the rotated by 2 squares, so I guess I must have a tick here as well. But then of course I want to get the same thing when I rotate it by 2 squares, so I should be able to rotate it by 2 squares again, so there should be a tick here. And then I should be able to rotate it by 2 squares again, so there has to be a tick here as well. That was a bit subtle because it goes off the edge, but when I glue it together there isn't an edge. And then finally I have to be able to rotate it 2 squares again and get the same thing, so there has to be a tick here as well. So the ticks kind of imply each other. There's a structure going on there which is to do with the fact that 5 is prime, and to do with the fact that as I'm adding on 2 squares, I'm looking for a multiple of 5. That's really what's going on behind the scenes. Okay. A question about applications, which I can do in a second. Personal statements. A bit like roots of unity. Yeah, I guess roots of unity are also about rotating things around. Roots of unity are worth an internet search if you haven't met them before. One person says that makes sense. I wonder if it was the person who asked the question. That'd be nice. And I've got kind of 3 admissions questions that I'm going to do. I think, let's go through these. Math computer science applications work the same as other applications. You have to sit the mathematics admissions test. For more information, search for ox.ac.uk/apply. They've got information about how to apply. Or if you can find the computer science website, they've got loads of details about how their applications work. What do we love on personal statements? We like it when people have looked a little bit beyond the classroom. For example, if you've been to some sort of after-school maths club on YouTube, then you could talk in your personal statement about what you got out of that, how it helped you prepare, what it made you think about, what you went and tried afterwards. Because I think the best sort of extracurricular mathematics is ones where you get shown something, but not everything. So that there's something left for you to wonder, something left for you to find out yourself. If you want to try doing that, then we've got about 50 back episodes on this show of things that you might be interested in. I'm not saying you have to watch our show, so there's not a plug for subscribing to the channel or something, but one of the ideas of this show is that we try and show people stuff that they might like to talk about in their personal statements, looking for people who would be good on the maths course. Is this what maths at uni is like? Or are the explanations a bit more complete? The explanations are much more complete at university. One of the big differences is that in a maths lecture at university, we go through every case. I've got the luxury here of not having very much time, which means that I can just show you kind of the ideas or the bits that I think are interesting, and just try and show you the tip of the iceberg, so that you can go and work out the rest of the stuff, or learn the rest of the stuff at university or something instead. The thing that we're dancing around in a lot of these recent episodes is ideas about symmetry and group theory, and normally when that's taught at university, it's taught in quite a formulaic way. It's sort of taught in a way that builds a lot of theory. What I've been trying to do is to show you different things that end up being sort of similar, vaguely similar sorts of theory, so that if one day you go and learn abstract group theory, then you've already seen some of the kind of shapes that it makes. If you get rejected from maths and computer science, do you get considered for standalone maths and computer science? I suppose so, in some sense. It's possible to get made an offer for maths or for computer science if you've made a maths computer science offer. It's not very common though. It happens less than 5 times a year, maybe less than 3 times a year, fewer. How important is work experience for the personal statement? For maths applications, we don't expect you to have work experience. I'm not even sure what that would be for mathematics. Same for maths and computer science. We don't know what that work experience would consist of. So I think my attitude to work experience is summed up by these rows of Pascal's triangle of just meh. If you can do something that's relevant and you can show us how it's relevant, then go for it. Sounds fun. I sometimes say I don't have any work experience. That's kind of not true now that I've been doing this job for a bit, but I didn't have any work experience when I went to university. What sort of jobs does it lead to? Loads of things. Because our grads have shown that they're good at solving problems, good at learning new stuff, good at thinking logically, good at really a lot of different transferable skills. Lots of graduate employers are quite keen to take our grads and teach them a bit about computer science, or teach them a bit about coding, or teach them a bit about finance or consultancy or teaching. Just teach them a little bit, and they learn that quite quickly, because our grads have shown that they're pretty good at picking up new stuff and applying things to complex situations. If I didn't plug the channel at last week's seminar, some of us wouldn't be here. Oh my goodness. So I did a webinar last week. It was last week's webinar. Who did I do a webinar for last week? I do too many of these. Question in chat, should you do all 3 admissions tests? Sort of like collecting the infinity stones, right? That reference is quickly becoming out of date. You only need to do the MAT if you're applying to particular courses. So Oxford uses the MAT, Imperial and Warwick also use the MAT for some courses. Otherwise, don't do the MAT. Tamua is used by some universities, but maybe Matt might have covered some of the ones you're interested in. Maybe you'll do Tamua as well. It's a bit of a shame to do both, I suppose. STEP you only need to do if you're applying to particular universities. I think Cambridge and Warwick use STEP, maybe some other ones, and if they ask you to. So I don't think there was a word "should" in there, which I don't love. But otherwise, yeah, do them if you need to. That's how I would approach it. Do them if you need to. You can access past papers. Right, cool. We've gone a little bit over because it's the last one of the season. Someone here applying for CS. If you email the undergraduate admissions inbox for computer science, should be quite easy to find them. If you find CS Oxford, if you email them, they should be able to help you with specific computer science questions. I've now got video evidence of me passing the responsibility onto their inbox. Hi CS. When's when does this sort of maths on Thursday return? Great question. We are back on the 20th of April, so 3 weeks from now. I have not converted that to hours. I didn't plan this through. Hurried search. Oh yeah, great. We'll be back in 503 hours for another episode of the Oxford Online Maths Club starting season 6. In the meantime, I've got an image. We've got many past episodes that you might be interested in. We've got history podcasts, we've got infinity podcasts, a history episode, we've got an infinity episode. We talked about pentagons, powers, Pascal's triangle again, symmetry, fitting triangles and squares, Truchet tiles were absolutely brilliant. We talked about inversion in circles, we talked about graph theory, we've talked about infinity and surreal numbers. We've talked about Zeno's effect, and we've been counting things quite a lot. We've been counting things in Pascal's triangle and counting cubes. All those episodes from season 5 are available on the Maths Club website, link in description and on screen if you don't have access to the comments. But we'll see you in 503 hours for another episode of the Oxford Online Maths Club. Bye.